This robot plays Jenga, fully automated using a custom motion system, sensors, actuators and software. And we built it for less than 150 euros using 3D printing and cheap off-the-shelf components. In this video, I'll show you how we designed it and share our learnings so you can build your own robots and low-cost automations at home. Hey, my name is Jan from JanTec Engineering and I study electrical engineering at the Technical University of Darmstadt. Last semester, I attended a project called Practical Engineering Methodology, or PEM for short. The goal is to teach actual engineering projects. Students get split into groups of 6, each working on the same problem. There's a dedicated lab with some basic tools and 3D printers. This year's task was to develop a robot that plays Jenga, but in a simplified way. It only has to detect loose bricks and remove them. It must not lay them back on top. The boundaries were really tight. We had a given board where the robot had to fit on and a limited power supply. The budget was 150 euros, basic screws and standard PLA filament were provided, but every single component you ordered counted into that budget, even if it was a prototype or unused test part that failed. Now let's get to how we designed and built our robot. The idea was to have a system that can rotate 360 degrees around the Jenga tower, so it can reach the blocks from any side and adjust if the tower shifts or rotates. This is what we came up with. Let's go through it part by part. To keep the weight of the Z-axis as low as possible, the gearing was mounted at the bottom, driven by a stationary NEMA 17 stepper motor. Instead of buying a large, expensive bearing, we used cheap, regular 6 or 8 bearings and integrated them directly into a 3D printed rail. In the Z direction, a ring-shaped gantry moves vertically, driven by a low-cost belt and a NEMA 17. This design is way lighter and more cost-effective than lead screws. Thanks to a dual clamping system on the left and right, the gantry can be perfectly adjusted so it doesn't tilt. The motor itself is stationary and centrally positioned at the top, hidden away and secured through slotted holes, which also makes it function as a belt tensioner. Below the gantry, 2 time-of-flight sensors are mounted to align the robot perfectly parallel to the row of blocks. There is also the X-axis, which is used to precisely reach each of the 3 blocks in a row. This was one of my main tasks, so I can tell you a bit more about the design decisions here. We used 4mm silver steel rods, as they sell for only about 4 euros per meter, take up very little space, are lightweight and can be easily cut to size. The left and the right holders fit perfectly under the Z gantry and feature press-fit holes for the rods, as well as an integrated belt tensioner using a self-locking nut. To reduce costs, the X gantry glides directly onto the raw rods without any expensive linear bearings. If you want to learn more about my personal iterative design process, I made a full video showing how I designed this exact part and improved it step by step in strength, printability and tolerances. In the end, this design allowed for very smooth and precise movements. The so-called measuring axis gets mounted right onto that X gantry. The idea here is to tap the stones and check if they are stuck or loose. For this, I first needed to learn how to design a rack and pinion in Fusion. I did multiple prototype test prints until I found the correct dimensions and settings, and then integrated it into a motor holder with an integrated guide rail so nothing falls out. Such a beam load cell mechanically connects the rack to the pushing mechanism so that the force occurring when touching a block can be properly introduced and measured. I used a little test jig while prototyping to verify that this load cell setup was precise enough to measure the force at the bricks. Turns out it is. The pushing mechanism itself consists of an MG996R 360 degree servo motor, which also moves a rack linearly using a 3D printed gear. This rack is designed to be able to push all the way through the tower, a full 80 mm, in order to safely remove the blocks. Here are some tips and learnings from designing this system in CAD. When you start designing a bigger or more complex project, dividing the problem into sub-problems is a good advice. Also, celebrate small achievements to keep yourself motivated. Most importantly, define your interfaces early on. An example of this would be the mounting holes in the Z gantry, where the time of flight sensors and the x-axis attach. This helps immensely, especially when working in teams like we did. Another tip is to get CAD models for used components from online libraries like GrabCAD or from the manufacturers themselves. This way you can work with your physical hardware, like motors, end stops and sensors, directly inside your CAD assembly, get dimensions easily and test the fit before printing. As I mentioned, for my designs, I usually go with an iterative process by running quick tests for a proof of concept, defining a minimum viable product, and then improving it until it fits into the whole robot. Check out my dedicated video on that if you're interested. Now, the PCB was made using KiCad. I wasn't directly involved in that part, so I can't tell you every detail, but we made some important design choices here. We didn't use any SMD components, meaning everything is through-hole and can be easily soldered by hand. This actually came in super handy when we accidentally installed the wrong capacitors. Desoldering them was totally doable. Using JST connectors was great for securing safe poka-yoke connections, but I have to admit, crimping all these individual wires was an absolute pain. We also left the system quite open by adding a lot of test points across the board and using hardware switches. For instance, to select between the standard step direction interface and UART for the TMC drivers. This kept everything as modular as possible. The firmware was built using the Raspberry Pi Pico Arduino core, and it's split into two parts that run simultaneously on the two separate cores of the RP2040 chip. One core is exclusively responsible for controlling the TMC drivers and reading the end stops. This ensures that there are absolutely minimal timing delays between signals in this loop. The second core is responsible for all the other tasks, such as reading the sensors, planning the next moves, and calculating the exact positions of the axes. Because both programs access the same RAM, they communicate perfectly. A large part of this software structure is implemented using clean state machines driven by state, enum, and switch case statements. So that is, briefly explained, our whole robot. Before we test it, quick thanks to the channel supporters. Prusa Research sponsors my studio. They provide printers and filaments so I can do all these tests and projects. PCBWay supports this channel and allows me to order complex parts I simply can't print in my home lab, like CNC machined or turned metal parts, custom PCBs, and high quality SLS or SLM 3D prints. In theory, I could even get sheet metal or injection molded parts from them, though I haven't tried it yet. I highly recommend PCBWay for projects like this one. You can get custom PCBs, like our mainboard, for just a few dollars. Check out PCBWay.com if that sounds interesting to you. Now let's see how our robot actually performed. Overall, the mechanical implementation met all the basic requirements. Its motion system is incredibly precise, allowing the robot to flawlessly reach and position itself at any spot in the tower to test and remove the blocks. But when it came to the actual competition, things didn't go entirely as planned and we ran into a few struggles. The main problem occurred when pushing out the blocks. During the pushing process, the blocks sometimes rotated slightly. I quickly designed a slide on the opposite side to catch the pushed out block and prevent it from dragging the row above it down. It still didn't work out perfectly. In retrospective, I think we focused a bit too much on building an over-engineered platform rather than solving the specific problem as simple as possible. To give you an example, the group that actually won the competition built two rather simple Z-axes with a static array of little shooters, each to shoot the stones out. Their robot couldn't react to rotation of the tower, but they didn't need to. Their mechanical setup was so precise that it never even caused the tower to rotate. It was a highly problem-specific solution and honestly probably the best approach. Back to our robot. In the end, the total cost was about 117 euros or 135 US dollars. Even if you would count the filament and standard screws in, the total cost would be way below 200 USD, which I think is pretty good. It might not have won the grand trophy at the competition, but taking a complex automation problem, managing the constraints and watching it push a block on its own makes the entire process worth it. A huge shout out to my group members for the amazing teamwork. I think the skills and workflow we learned is incredibly valuable, also for home projects. You can be your own client, set your own budget and use tools you probably already own, like a 3D printer and some basic screwdrivers. I think it's absolutely wild that today, with a bit of time and a small budget to spend on a store like AliExpress, you can build a full motion system with sensors and custom actuators at home. If you like this kind of low-cost robotics, I highly recommend checking out Thomas Sandladerer's video on his 3D printed Caroline robot arm. It's an awesome project. Thanks to my channel members and see you next time here at JanTec Engineering. And if you're wondering why I'm here and not in my studio, that's because I'm currently in Japan, Okinawa to be precise. In about 1 week, the Japan Rap Festival is going to take place in Tokyo and I'll be there as an exhibitor with my friend Hendrik, the electroplating legend. If you can make it to the event, definitely come by and say hi.